Good morning, students. Our today's topic is self-adjoint, unitary and normal operators. So let us define what is self-adjoint operator. If we have a bounded linear operator T defined on a Hilbert space H, then we say that this operator T is self-adjoint or Hermitian if the Hilbert adjoint operator of T, which we denote by T star, that is same as T. So the operator T is self-adjoint if T is same as T star. Here T star is Hilbert adjoint operator of T. Now second is this bounded linear operator T defined on Hilbert space H is said to be unitary if T into T star is equal to T star into T is equal to identity, or we can say that T is bisective and T star is equal to inverse of T. Then we say that the bounded linear operator T, that is unitary. Next, this bounded linear operator T is said to be normal if T into T star is same as T star into T. Now next is a property, because for a Hilbert adjoint operator T star of the operator T, we already discussed inner product of Tx with y is equal to the inner product of x with T star y. Now if T will be self-adjoint, in that case T star, that is same as T, so this property will become inner product of Tx with y is same as inner product of x with Ty. Now next property, if T is self-adjoint or unitary, then T is normal. So firstly let us take T is self-adjoint. Now by definition, if T is self-adjoint, then T star is same as T. Now let us consider the inner product of T star x with x. Now by the properties of Hilbert adjoint operator, we can write this as, by taking T in the second argument, this will become inner product of T star x with T star x. So by definition this will become T star x norm square. Now because T star is same as T, so this is further is equal to Tx norm square. Now by definition Tx norm square means inner product of Tx with itself. Now again taking T in the first argument of the inner product, this will become inner product of T star Tx with x. Now because this is true for every element belonging to the Hilbert space H, so this implies that T star is same as T star into T, and this is a condition for the operator T to be normal. So this proves that T is normal. Now next we show that T is unitary. Next we show that if T is unitary, then T is normal. So we are given T is unitary. Now by definition of unitary, T star is equal to T inverse, and we are to prove that T is normal. It means T star is equal to T star T. Now let us consider T into T star. Now because T star is equal to T inverse, so this will become T into T inverse. So that will be identity. In the same way, if we consider T star T, then that will also be identity by using this property. So this proves that T is normal. Thus we have proved that if T is self-adjoint or unitary, then T is always normal. But the converse is not in generally true. Means if operator is normal operator, then it need not be self-adjoint or unitary. Let us see an example to show this. Let us take identity operator defined on the Hilbert space H. Then we show that the operator T defined by 2 iota into I, that is normal. To show this T is normal, let us prove that T into T star is equal to T star into T. Now, as inner product of Tx with x is given by inner product of x with T star x. Now, substituting the value of operator T is 2 iota into identity. Substituting the value here and taking 2 iota outside from the first argument, we get inner product of Ix with x is equal to inner product of x with T star x. Now, we can take this scalar in the second argument, so that will become conjugate. The conjugate of iota, that is minus iota. So from here we get inner product of x with minus 2 iota x is equal to inner product of x with T star x. Now from here this x can be written as identity of x, because identity of x is same as x itself. So from here we get T star is equal to minus 2 iota into I. Now let us find T into T star, substituting the value of both T and T star. So this will be 4i, and T star into T, that is also 4i. So both are same. So we can say that T is normal operator. Now we will show that T need not be self-adjoint or unitary. Now because T is 2 iota into identity and T star is minus 2 iota into identity, both are not same. So T is not identical to its Hilbert adjoint operator. So T is not self-adjoint. Now we show that T is not unitary. Now T into T star and T star into T, these are not equal to identity. So T is not unitary. Next we will prove the self-adjointness property for the operator T. If the T from Hilbert space H to itself is bounded linear operator on the Hilbert space, then we are to prove that if T is self-adjoint, then inner product of Tx with x, that is real, and this is true for every x belonging to the Hilbert space H. And the converse of this is also true if the Hilbert space H is complex. It means if H is complex and inner product of Tx with x, that is real, then the operator T is self-adjoint. So let us prove this property. So in the first part we are given T is self-adjoint. By definition of self-adjoint, T is same as its Hilbert adjoint operator T star. Now let us consider for every x belonging to H the conjugate of inner product of Tx with itself. Now by the conjugate symmetry property of inner products, this can be written as inner product of x with Tx. Now this T can be taken in the first, now because T is same as T star, because T is self-adjoint, so we can replace T by T star. Now taking this in the first argument, this will become T, so we get inner product of Tx with x. So the conjugate of inner product of Tx with x is same as itself, and if the conjugate of a number is same as itself, then it is real. So we can say that inner product of Tx with x, that is real for every x belonging to the Hilbert space H. Now we will prove the converse part. Now in the converse part, that holds if H is complex. Now we are given H is complex and inner product of Tx with x, that is real. Because this is real, so its conjugate will be identical to itself. So from here, now shifting this in the second argument, this will become T star. So this can be written as by taking this term to the left side, this will become inner product of Tx with x minus, by property of conjugate symmetry, this will become inner product of t star x with x is equal to 0. Now this can further be written in this form by using the properties of inner product. Now we can use zero operator lemma. According to zero operator lemma, if the inner product of qx with x is 0 for every x belonging to h, then the operator q itself is 0. So here this is a bounded linear operator, and because this condition is true for every x belonging to h, so by zero operator lemma this operator itself be zero operator. So t minus t star, that is 0. So we get t is equal to t star, and this proves self-adjointness of operator t. Now next we prove the self-adjointness of the product of bounded linear self-adjoint operators. So the product of two bounded self-adjoint linear operators S and T on a Hilbert space H is self-adjoint if and only if the operators commutes, means S into T is equal to T into S. Now because S and T, these are bounded, so their product will also be bounded linear operator, and also S is self-adjoint, so its Hilbert adjoint operator S star will be identical to S. T is also self-adjoint, so the Hilbert adjoint operator of T means T star, that is also T. Now by definition, S into T, that will be self-adjoint if and only if its adjoint is identical to itself. Now by the property of Hilbert adjoint operator, this can be written as T star into S star, and this is ST. Now T star is equal to T, S star is equal to S. So from here we get TS is equal to ST. So we can say that the product is self-adjoint if and only if S and T commutes, and this proves the self-adjointness of the products. Now the last property is the sequence of self-adjoint operators. If we have a sequence Tn of bounded linear self-adjoint operators on the Hilbert space H, and the sequence Tn that converges to T, means Tn minus T norm approaches to 0 as n approaches to infinity. Here this norm is defined on the space of all the bounded linear operators. This is the space of all the bounded linear operators which are defined on the Hilbert space H. Then we are to prove that the limit operator T, that is also bounded self-adjoint linear operator. So this theorem is divided into three parts. We will prove that T is linear, T is bounded, and T is self-adjoint. Now, so our first part is to prove that T is a linear operator. Now to prove this, because this is the space of all the bounded linear operators, and this space, that is a complete norm space. Complete norm space, that is also called Banach space. So every sequence Tn which is of bounded linear operators in this space, that is convergent in the same space. Now here, because Tn converges to T, so the limit function that will also belong to the same space. It means T will also be bounded linear operator. Now we prove that T is linear. To prove T is linear, let us take two elements x and y from the Hilbert space H, and also two scalars alpha and beta. Now to prove T is linear, let us find the image of alpha x plus beta y under T. Now by definition, because T is the limit of sequence Tn, so this can be written as limit n approaches to infinity Tn alpha x plus beta y. Now this can further be written in this form. Now because Tn converges to T, so this will become Tx and this will become Ty. So we get the image of alpha x plus beta y, that is equal to alpha into image of x plus beta into image of y. So this proves that T is linear, and we already proved T is bounded. Now finally we proved that T is self-adjoint. Now to prove that T is self-adjoint, we have to prove that T is equal to T star. So let us consider the norm of T minus T star. Now this can further be written as T star minus T norm. Now adding and subtracting Tn star and Tn inside and applying the triangle inequality. So this will be less than or equal to T star minus Tn star norm plus Tn star minus Tn norm plus Tn minus T norm. Now this can be written as T minus Tn whole star norm, and we know that the norm of Hilbert adjoint operator of a bounded linear operator is identical with the norm of that operator. So this will be same as T minus Tn norm. So this will become T minus Tn norm. This is also Tn minus T norm, and because Tn is the sequence of self-adjoint operators, so Tn star will be same as Tn. So this will become 0, and these two terms are same. So this will become 2 times Tn minus T norm. But we are given that the sequence Tn converges to T. It means as n approaches to infinity, this norm approaches to 0. So from here we get T minus T star norm is equal to 0. And because norm is non-negative quantity, if norm is 0, then the expression inside the norm, that will also be 0. So from here we get T is equal to T star, and this proves the self-adjointness of T.